Hi, in this video, we're going to be going over the relative strengths of acids and bases. So specifically, we'll talk about the difference in the term strong versus weak and how to identify that. We'll also go a little bit into the how to tell when something is stronger versus weaker, especially using the polyatomic ions and looking at what we call oxyacids. In addition, we will talk about weak acids and bases further, so we'll get more specific in how a weak acid and base is different from a strong acid and a base in terms of calculations. All right, so let's go ahead and get started. First, let's talk about the strengths. So when we use the term strength, one thing you want to be very careful about is to realize that strength does not equal molarity. Those are two separate things. So strength is actually, sorry, I went off my page on that. Strength is actually a physical property of my acid or a base, and it's based on its solubility or its position of dissociation. So the more it dissociates or the more soluble the acid or base is, the stronger it is. And so as we learned before, that's based on an equilibrium constant, which we use as a Ka or a Kb value in the case of an acid or a base. So when we refer to something as a molarity, remember molarity is moles per liter. And so that's how many moles there are dissolved per liter of solute. So I could have something that is really high concentration or high molarity, but it would still be weak. For example, one of the most common weak acids that we can have is acetic acid. I can have a really concentrated 12 molar concentration acetic acid, but doesn't matter, the acetic acid is still a weak acid overall. So a high molarity does not indicate a high strength. So when we're looking at the difference, you can kind of see here in the picture on the left that before dissociation, when we're talking about things that are strong are going to dissociate 100%. So here's my acid beforehand, and all I have are dissociated into ions after the fact. Don't forget your dissociation equation. This happens when I add it to water. And so in this case, it's an acid. And then I make H3O plus and the A minus ion. So something that is strong dissociates completely. We tend to refer to it as 100% dissociation is usually what we say. It's very close to 100%, even if it's not. And these are going to have really large K dissociation or K values in terms of equilibrium. So typically K is going to be greater than 1. You can kind of see a little picture down here that shows that in a strong acid, you only have ions present and you don't have any of the compound together. In a weak acid, though, and weak bases, it's the opposite. There is less dissociation. So there's only a slight dissociation percentage. And so in this case, it's usually less than 1%. So it's a very low percentage of dissociation. We would refer to these in solubility as insoluble compounds. However, with a weak acid, weak base, we still can't visibly see them. So they only dissociate a slight a bit. So therefore, my K values are going to be very small because it's going to be very reactant favored, meaning it is not going to break apart into the ions. So if we look at our picture over here on the left, we can see that we start out with that same amount of acid compound, but we can see that we still have quite a bit of the acid compound and only some ions floating around. In the picture that you see with the ions showing, most of those compounds are still intact and only a few ions are present. So be careful on making sure you understand that the strength of the acid is all about the degree of the dissociation, and that is a physical property based on the equilibrium value of those compounds. All right, so the other thing you want to be aware of, we've talked about this previously, but just to kind of hit it again, is the strength of our strong acids. So remember that there are really 6 strong acids that are agreed upon by the AP college board graders. So you have hydrohalic acids. Those are your halides. So those are the ones that we tend to think of, like very obvious, like HCl, hydrochloric acid, HBr, and HI. Notice on here, though, that HF is not included. That's important to recognize. The reason that HF is not included here. So if you look at this table right here down at the bottom, it has to do with the bond strength. So one thing you need to remember is when we're looking at bond strength, if it's a strong bond, so remember, to make a strong acid, we need lots of dissociation. So lots of H plus ions free moving around, which technically means very soluble is the best way to kind of think about it. It's not really a KSB, it's not a solid but it's always going to be lots of ions, okay? So if I look at my strength of my bond, if I have a strong bond, that means it won't make ions. So strong bonds don't break into ions or don't dissolve well. So therefore, if they don't break into ions, they're not going to be very good, so not very acidic. That means that they don't have very many H plus ions. So if we compare the HF right here, it's a really strong bond. So strong bonds means, and this is where HF would fall, it just means that the fluorine is a really small ion, and so therefore that creates a strong bond. So that means the hydrogen and the fluorine radii are closer to each other, and so therefore their bond strength or their attractive forces are greater, and so therefore there's very little dissociation. And so that is the reason of why the HF is considered weak. But then when we compare all the others, as I go down, these ions get larger. So for example, as I'm going this way, my ions get larger. And so the larger they get, sorry, that looks kind of messy, but the larger those get, the weaker that bond becomes. So that's why we see that decrease in bond strength. But that's really ideal for strength of acids and bases. If it's a weak bond, it's going to basically break apart and make lots of H pluses. So you want to make sure somehow in there that you know weaker bond means stronger acid. So somewhere in there, so weaker bonds equals stronger acids. So that's kind of what we're looking for. That's really important with the reason hydrogen fluoride. They like to use that as an example a lot. So you have to be able to explain why hydrogen fluoride is not a strong acid. And it's really important to make sure you don't mix it up and think it is. You've also got nitric acid up here as a strong. You've got sulfuric. We haven't really talked about it yet, but notice sulfuric has 2 hydrogens there. That's called diprotic. We're going to talk about that more coming up later. And then you've got perchloric, which is HClO4. This is actually one of your strongest acids there is. So if you had to pick the strongest one, then that's it. Sometimes the book will mention that HClO3, so chloric acid, and sometimes they'll say phosphoric or strong, but these are the ones that are kind of recognized that we will expect you to know for the AP exam. So when you look at those, you need to recognize that the strength of that acid is not the same thing as its molarity. It is a set, understandable, like known fact that these are my strong acids, and what you want to do is consider all others as weak. And so that makes your life a little easier when you just have to memorize these few. In terms of hydroxides, for bases, we typically say any alkali metal hydroxide is for sure strong. So alkali metal hydroxides, because those are very reactive, and are going to be in that strong category. We also typically include calcium through radium because those are very big. So calcium hydroxide all the way down to radium hydroxide. I don't even know if radium hydroxide actually exists. I've never seen it be used, but anything on there. But we tend to think these are going to be strong. And so they would produce lots of hydroxide. But what we tend to think of as, let me move over here since I wrote too big. We tend to think that with calcium hydroxide, all of those things, the main ones they'll give you that maybe are not, and then again, it's that same reason, beryllium hydroxide and magnesium hydroxide are actually weak. They're not very soluble, so they have a strong bond. Again, it's that same idea. So they're a weak acid, strong bonds, or weak base. I don't know why I just said acid. But yeah, so it's the same idea. These are very small atoms. And so since those radii of those ions are really tiny, then their attractive force is really small. So that keeps them really, really strong, tight held bonds. Another difference in strength that you kind of need to be aware of is with our what we call oxyacids. So an oxyacid right here is basically your hydrogen with a polyatomic ion. So like XO3, whatever it is. So it's hydrogen with the polyatomic ion. So anytime you have that, what happens is you have to be able to explain why the more oxygens that are present. So this is the trend. This is like the trend. You can memorize, but it won't explain it. So you know how when they ask you that justify or explain, this wouldn't be enough. So it says the more oxygen present in the polyatomic ion, the stronger the acid is within that group. So you have to be comparing the same ones. So for example, in the one you see down here, we're comparing the ClO4, ClO3, ClO2, ClO, or we're going to compare the SO4, SO3, so you can kind of see the difference. So the more oxygens you have, the more it pulls electron density away. This is because, so when I look at, let's see, this example, I'm going to use this example over here in the middle. So when I'm looking at these oxygens right here, what I can see is that this oxygen pulls away and pulls away and pulls away. So remember, oxygens are electronegative. That means they're going to pull the electrons in the bond towards them. So your electron density is going to come over here. And so then what's going to end up happening is your electrons are pulled away from this bond right here. Well, what's going to end up happening is that makes it really easy for this hydrogen to pop off. And so it makes it a lot easier because you're pulling the electron density away, which weakens that bond between that hydrogen on the other side. So when you're looking at what's going on, that added electron density weakens the bond. So more oxygens means more electron density. So if add more oxygens, you're increasing the density in the region that's opposite. So then that means that less energy is going to be needed if it's a weaker bond. So more oxygens, key here is more oxygens increases the strength because it weakens the bond. So again, it comes back to a weaker bond means a stronger acid or stronger base, in this case stronger acid. So you can kind of see in this picture over here on the left, it's showing you like how the electron density changes, and so it's kind of the reverse of what we see in this table. So here it's showing you so it's just showing you the chlorine pulling a little bit, and then here I've got the chlorine and the oxygen pulling, so that's going to be a little bigger, and then here I've got chlorine and oxygen, 2 oxygens pulling, chlorine with 3 oxygens. So we can just see the more oxygens we have, the greater that electron density becomes. And so this bond that gets weaker. So it's a weaker bond, which then means stronger acid. So this is really important to recognize because that's easy to compare. So for example, when I'm just comparing these without even looking, I can see H2SO4 versus H2SO3. I know this is going to be stronger because it's got more oxygens. And so this is considered one of my strong acids, whereas HSO3 is a weaker acid. obviously with a smaller Ka value. It still has a fairly large Ka value, just much smaller, obviously, than what H2SO4 is. And then if you compare the nitric versus nitrous acid, same thing. The more oxygens, when you're comparing them together, more oxygen is going to be much stronger. Moving on to the strong bases, I already kind of talked about this. With a strong base, the hydroxides or any type of hydroxide that is the 1A or 2A metals, with the exception of magnesium and beryllium, are going to be very, very strong. I think I called those acids. I'm sorry. Strong bases are considered hydroxides. So any 1A or 2A metals that are hydroxides are going to be very, very strong. And again, this comes down to solubility. So it's that same idea. Solubility plays a role. If they're really soluble, they're really strong. So for example, NaOH is very, very soluble. Remember, sodium is, and alkali metals are very, very soluble. So that means when I put this in water, it's going to break apart into its ions very well. So we'd have lots of Na plus aqueous ions and HOH minus ions, aqueous. So it's going to be 100%, just like we were seeing on the previous page. The stronger the acid, the weaker its conjugate base is going to be true. So that's important. That's a good statement to kind of be aware of. The stronger it is, its conjugate base, which is on the other side. So let's just use, I'm going to use HNO3 as an example. So if I'm looking at HNO3 and I have water and it dissociates into H+, which will be H3O+, because it's going to add to the water, and NO3. So when I'm comparing, we know this is a strong acid. And so water would then be technically acting as a base, and it's going to be a weak base in this case, obviously. But it is going to be accepting the hydrogen ions, right? And so then we see H3O+, which is obviously an indicator of an acid, right? And then NO3- over here is now a weak base. So it's not going to be a hydroxide, so it's not a strong base, but it still is a slightly basic effect because it does have the ability to accept hydrogen ions or protons. Another important thing to kind of, that kind of is what this chart over here is showing you, is that same idea. The stronger it is, and so this is the acid strength itself, and then you can see that it's conjugate. So when we're weak, we're kind of even. So a weak acid will have a weak conjugate usually. They're kind of about the same. And then we have a very weak acid will have a very strong conjugate base. So they always kind of go together. Trying to think if there's anything else. I like this little page that, this little description that says various ways to describe the acid strength. With your K values, those are important things to be aware of. So for example, with equilibrium, if something is strong, remember it's very, very product favored. So therefore it's going to be lots of H pluses. So that's going to be a high quantity of product and a low quantity of reactant. So that's why that one's a large Ka value, whereas a weak acid is going to be small because it's less H+, or basically in this case less product and so more reactant, so it's more reactant favored. The position of the dissociation far to the right, that means product favored. We talked about this previously, versus far to the left for the weak acid, which is reactant favored. And we've got the equilibrium concentration of H+ compared with the original. So these are going to be, this is kind of an important statement to recognize, is when you're looking at your concentrations of the two, these should be the same because all of this should be converted to this. So it should be 100%, pretty much, almost 100% converting over. So that's why those two are pretty much going to be equal. So we typically say if I have 1 molar, let's say HCl, which is a strong acid, then I pretty much know that I have 1 molar H+ and 1 molar Cl-, which really we only care about this one. But we can say that it 100% dissociates in the reaction, so Since it completely breaks apart, we've got 1 molar of each. Whereas with a weak acid, that's not going to happen. So if I had a weak acid, for example, with acetic, same thing. If I have 1 molar of this, it's only going to break apart a little bit, but it's going to prefer to stay this way. So if we think about how it's working, it's really going to be mostly this direction arrow-wise. It would be like a little arrow this way, like that kind of. And so we would have a little bit of H plus and a little bit of C2H3O2 minus, or that anion. But when I'm comparing, if this is 1 molar, this is going to be like 0.0001 molar of these. So it's going to be really, really tiny concentrations. So it's not producing as much. So the hydrogen concentration is a lot less than what your original concentration was. And then your strength of your conjugate base compared, we said that already, is just reviewing that your conjugate is the A minus, is much weaker than the base, is a weaker base than the acid would be. And if it's a weak acid, it's going to be a stronger base. So they're always going to be opposites of each other. So just, that's kind of a memorization fact you need to know. All right, so on this page, we're going to talk specifically about weak acids and weak bases. So weak acids and weak bases include most everything. So that is kind of important to recognize. When we're talking about weak acids and weak bases, there's way more of those than there are strong acids and strong bases. So this means they're not going to ionize very much, so they're going to be very reactant favored. So we want to keep that in mind. They're also going to have K values that are less than 1, so that kind of idea. Means the equilibrium established, and far to the left, the equilibrium expression for acids is known as a Ka, versus the bases are known as Kbs. So when you use a Ka expression, one thing that you want to be very clear about is that we still use this arrow right here for equilibrium, and we still set up our equilibrium expressions the same way. So this is my generic equation for an acid. Now, when I see that equilibrium sign, that usually tells me it's weak. If it was, sometimes they can put it that way for a strong, but typically, if you were really thinking about it, if it's a strong acid and we put that in water, I mean, it's 100% dissociation. So it's pretty much just a right arrow to make H3O plus and A minus. So remember that 100% dissociation in a strong will typically mean that it's very product favored. So when it's a weak acid, it's set up just like any other equilibrium expression, products over reactants. One thing to notice is we are eliminating out water because it's a liquid. So we do not include solids or liquids and inert gases in our equilibrium expression. So it says many common weak acids are oxyacids, so like phosphoric and nitrous. Other common weak acids are organic acids, so you may get some like big crazy groups. They look weird, but you treat them just like any other acid. You look for that hydrogen that it's going to lose, and everything else stays intact. And then you adjust your charge as needed. So if I lose 1 hydrogen ion, then my charge goes down by 1. So then you can kind of see your H3O plus, your A minus, and again, it would be to the coefficient of whatever power it was. So if it wasn't a 1-to-1, and then your products or reactants on the bottom. So products over reactants. And as it told you earlier, it should be less than 1. So we are looking for it to be much less than 1. So these are just like a regular equilibrium problem. So we're thinking of them as not being very soluble, or they don't really dissociate very much. And so that's why we treat them as an equilibrium. We don't need to do this for a strong. So for a strong, it's assumed it's 100%, so there's no reason to worry about that. We know the concentration of one tells us the concentration of the other. So for example, it gives you a table here with some Kas. One thing to notice is the strength of the acid. So if you notice here with your Kas, the larger the Ka value, so larger Kas equals stronger acids. So you could put things in order based on their Ka values. If I wanted to write the equilibrium expression for, the acetic acid. So a Ka expression, we would have to first write our equilibrium, our reaction. I typically write most of my reactions as the generic equation because it's always going to kind of be the same. So you've got HA and water are always going to be making the H3O plus because it's donating that hydrogen over, and the A minus. Well, the A minus is whatever the other thing is. So for example, in that one, it's the sulfate. In this one, it's ClO2 minus, or the C2H2 ClO2 minus. So when we take off the hydrogen, that's what the anion always is. So for acetic acid is this one right here. And here's its Ka value. And so really all we're going to do is we're just going to substitute in, instead of HA, we're going to write HC2H3O2. And it's neutral because it's the compound. And so when I add that to water, it's weak, so therefore we know it's going to be at equilibrium. And so it's going to make H3O plus and the acetate ion, which is C2H3O2, and then minus, because it was a +1, -1 originally. So when I take away the hydrogen, the ion left behind is a -1. To write the equilibrium or Ka expression for this, my expression is going to be that the Ka, I have to use the actual Ka value. I'm going to move it over here. So it would be the Ka, which is going to be 1.8 times 10 to the -5 will equal, and its concentrations, because these are all aqueous, so there'll be no pressures, and so it'll be products, which will be H3O plus, and in this case, everything's to the 1, so that makes it kind of easy. And it'll be C2H3O2 minus. Make sure you're including your ion symbols on that, because if you don't, you're going to lose points or they won't give you credit because your ions are not the same thing as your neutral compound. And then over reactants, which is going to be HC2H3O2. And then don't forget to omit the water because it's a liquid, so its concentration is like 55.5 molar or something crazy large because of the quantity. So this would be your EKA expression. Weak bases without hydroxide react with water to produce a hydroxide. This is like ammonia. That's the most common example. We talked about this previously in class. Methylamine. So sometimes you'll see these bigger methylamine, ethylamine. Sometimes they'll use these larger organic compounds. Don't let those freak you out. It'll usually tell you if it's a weak base, but it says the lone pair in nitrogen forms a bond with hydrogen. This is where we were discussing in class. This is a Lewis base. Because the nitrogens are always going to have a lone pair to donate. So whenever we see that nitrogen on the compound, that usually indicates that it's going to be almost 99% of the time, it's going to indicate it's a base. So anytime you see that, so that's what we're seeing right here is there's your lone pair that you have. And so what's going to happen is when it comes to the water, it's going to end up forming a coordinate covalent bond with this and leaving the hydroxide out. So it's able to pull off the hydrogen with the strength of its electrons. So these are just different ones. So you can kind of see, if you look at all these examples, they all have nitrogen with that lone pair. So that's why. That lone pair on these types of compounds are always going to pull off a hydrogen, or more likely to pull a hydrogen off of the water, and it's going to act as bases. All right, so if you see that, that's a good thing to kind of recognize. So that'll kind of cut you down on a little bit of time and make your life a little easier to recognize that. So those are general things you need to know for the weak base. And so the weak base equilibrium expressions are the same thing, except for instead we're using a Kb. So one thing to be really clear about, when you use a Ka, the product, you must have, as a product, you must have the H3O plus. So you want to make sure that you've got H3O plus, that hydronium ion, or H plus if you prefer. If you're using a Kb expression, then your product is a hydroxide. So that's the difference in them. And they're reversed of each other. So they're the opposite So if you have a strong base, remember its conjugate is a weak acid. So that kind of tells you that information. So for weak base reactions, here's your generic equation. So notice that the base takes one of the hydrogens. We talked about this before in Bronsted-Lowry, leaving the HB plus or that conjugate. So here's my base. So then this is my conjugate acid that's weak, and the hydroxide, which is obviously your base. Comparing those. So your conjugate base, which is going to be a little bit stronger. And water in this case is acting as an acid because it's donating. So your equilibrium expression works exactly the same way. So your products, which are your, in this case, the HB, goes up here. The hydroxide comes here. And then this base comes down here. So that was the reactant that goes on the bottom. And again, just like before, it's going to be less than 1 because it's very reactant favored. So we're going to see that we're making less hydroxide in this case. If it was a strong, we would do the same thing as I had said before. The strongs are definitely going to break apart into the hydroxides. It's very obvious because they're going to have the hydroxide in their compounds. So if we move down and look, kind of the same idea. KB for some common weak bases, here's the ones provided. It's showing those same examples we gave on the previous page. Write the KB expression for ammonia. So in this case, we need to write our reaction for ammonia. So it's going to be NH3, and that NH3 is going to react with the water, and because it's a base, it's going to accept one of these hydrogens. And that's also because it forms that coordinate covalent bond we talked about. So that'll be NH4 plus, and the hydroxide left behind. So then when you go to write your KB expression, you're going to make your KB, which is for ammonia is 1.8 times 10 to the negative 5, equal to my products, which is NH4 concentration. So NH4 plus and OH minus over my concentration of NH3. So we can see that the KB expression, it works the exact same way, products over reactants, but instead we're looking at the hydroxide concentration is usually what we're finding instead of H3O plus. So they do look very similar. The difference is the base, same thing I'd pointed out, the base produces the hydroxide ion in the solution, whereas the acid produces the hydronium ion in the solution. Also make sure that I know I've said it, but just to repeat it, these are equivalent terms. They mean the exact same thing. I usually write the water in my equation just because I think it makes it a little bit easier to see, and that's how I was taught to do it. But you typically can leave the water out. So water is very important, causing the acid dissociation, which is probably why my professor taught me that. All right, so what I want you to do is take a few minutes. I want you to use the table that were provided. I want you to look up the Kas of each of these, with the exception of water because it's neutral. So I want you to look up the Kas. And so this one says to put them in order according to their strengths. So remember, that's the opposite. So if we find the Ka values, the Kas are for the acid strength. So then it would be reverse for the bases. Reverse for bases. So look those up real quick and see if you can identify and put these in order from weak to strong bases in terms of the base. The answers are down here, but be able to explain that, and we'll talk about it in class when we get to class.